A very warm good morning to respected dignitaries, Honorable Principal Madam, MD Sir, Correspondent Madam, Director Madam, resource persons, co-conveners of the program, and all the participants of the Faculty Development Program. On behalf of Gates Institute of Technology, Department of Humanities and Basic Sciences, I, Dr. G. Haripriya, Professor in Mathematics and Head of the Department of Humanities and Basic Sciences, would like to extend a very warm and a hearty welcome to each of you for this one-week online faculty development program on advanced materials and processing and characterization methods. I thank you all for being here on this virtual platform. The world is full of diamonds and gems, and we're having some of them here today to build this event. With this note, I would like to welcome our resource person of our FDP, Dr. R.Padma Suvarna, Professor of Physics, Director and Sponsored Research at JN2A, who is an expertise in this area, and our special thanks for accepting our request to share her knowledge with all of us. I welcome our legendary Managing Director, Sri G. Raghunath Reddy Garu, lovable correspondent, Srimati V.K. Padmavatama Garu, our honorable director, Srimati V.K. Srivani Garu, and our beloved principal, Dr. Syed Surya Garu. And I thank them for giving their valuable time for us in spite of their busy schedules. I would like to thank you all for taking the time out from your busy schedules and making this spectacular morning with your glorious presence on this virtual platform. The objective of this FDP is to educate young teachers and research scholars about advanced material processing and characterization methods. The FDP is informative on material processing and advanced composites processing techniques. Advanced materials processing and characterization methods is a field of pure physics consisting of the study of the properties, material preparation, and characterization, which is the basis for all branches of science, engineering, and technology. Material characterization methods such as X-ray diffraction, SEM, TEM, UV visible, Raman, X-ray photoelectron, FTRI, and various synthesis processes that are used for the emerging materials. This program will enlighten the properties, material propagation, characterization, and applications in various fields involved in physics. Without taking much of your precious time, I will begin the program. Now, I request our beloved in charge principal, Dr. Shanti Madam, to address the session.
A warm good morning to the respected dignitaries, Managing Director Sri Raghunath Reddy Garu, Director Madam B.K. Vani Madam Garu, and Correspondent Madam Srimati V.K. Padmavatama Garu. At the outset, Gates Institute of Technology was established in the year 2001, which is affiliated to JNTUA Anantapuramu and accredited by NAC and NBA. The institution also got autonomous status and recognition of 2F and 12B from UGC. Institution is certified by ISO. The focus is to inculcate continuous learning habit with positive attitude and ethically sound values within the faculty and students. The institute has always envisioned instilling life skills among the students through their participation in various curricular extracurricular and co-curricular activities. Progressive thinking of our late correspondent Sri V.K. Sudireddy Garu has made Gates stand tall as one of the very first and few educational institutions to completely run on solar power. Institution is headed by dynamic managing director Sri G. Raghunath Reddy Garu, correspondent Srimati V.K. Padma Garu, who is the heart and soul of our institution, and director Srimati V.K. Srivani Garu, who is giving us in a new directions to the institute. Now, I welcome Dr. Padma Suvarna Garu, Professor Physics. He's also Director in the research side. And also, I welcome all the eminent professors who are who are with us for this 5-day FDP program materials. And also, I congratulate the team of Humanities and Basic Sciences because on this February 28th, it is a Science Day, which is also the markable event for this institution. Now, with this speech, I want to say one thing to the speaker, the research persons, resource persons, and the lecturers and the faculty, such that make use of this professors' interaction and interact with all the clarify your doubts so that we'll be in turn helping our students go in the research area also. I once again welcome Dr. R. Padma Suvarna Garu to be with us for this day session. Thank you, madam. Thank you for accepting us the invitation. Thank you, madam. Now I go on to the next one. That is, I'll give on the speak to the Haripriya so that for continuing the next program. Thank you.
To welcome the backbone of our college, our lovable correspondent, ma'am, Srimati V.K. Padma Garu, to please address the participants.
Hello. Good morning to all on this occasion. I am V.K. Padma, correspondent of Gates Institute of Technology, Gutti. Welcome you all to a 1-week FDP program on advanced materials processing and characterization methods. As you know, teaching profession is an evergreen learning field. We have to improve our knowledge, the new technologies we have to know, needs the regular refreshing courses to enhance teaching and research. This FDP is of this kind, which focuses on synthesis and processing on innovative materials. It benefits both the students and the faculty to develop their own simple devices for their projects. I thank today's speaker, Dr. Padma Suvarna Garu, Professor joined to you, and the research side eminent personality. And I once again thank you, madam, for accepting our invitation. And it is a very pleasure to all to share with your knowledge and the experience such a great personality. And I thank the other professors also. They are also accept, and We are thanks to them also. I thank the all organizers of our college and of the department. This kind of programs has to be continued practices. Okay, thank you, madam. Once again, use it in a proper way, and this will help to the students community and the faculty also. Thank you all.
Thank you so much, ma'am, for your kind words, ma'am. I hope you will have a stimulating and productive program over the next few hours. I would like to appreciate the questions put forth after the completion of this session in the chat box, and hence all the questions shall be answered. I will conclude my address with an additional call to all of you for active participation during the session. Now it is time to introduce today's speaker, the empowered woman is powerful beyond measure and beautiful beyond the imagination. I'm super happy to introduce the resource person of this FDP. She is none other than Professor R. Padma Suvarna, Professor of Physics, Director and Sponsors Research at JNTUA. Now, I would like to invite Mrs. Angeline Rebecca to read the profile of our resource person.
A pleasant and warm good morning to one and all. I am Angeline Rebecca, Assistant Professor in English. Welcome you for this one-week FTP on Advanced Material Processing and Characterization Methods. Now, I feel privileged to introduce Dr. Padma Suvarna, Professor of Physics, Director and Sponsored Research at JNTUA. Ma'am has completed her master's degree in physics at SK University, Anantapuram. She completed MPhil at the same in the SK University. Ma'am has completed her PhD in physics at SK University, Anantapuram with the title Material Science and Electronics. Ma'am has 26 years of rich experience. Currently, ma'am is working as a professor in physics at JNTU College of Engineering. Apart from being a professor, ma'am performed many excellent roles as a head of a physics department from 2011 to 2022 at JNTUA College of Engineering. Also, BOS chairman and a subject expert for paper setting and evaluation also. Ma'am has been working as a director and sponsor research from 2022 to till date. Ma'am has published 67 research papers, among them 22 are national, 45 are international. She successfully guided 16 PhD scholars. She published 7 books. She has organized and attended many FDPs and workshops and also conferences. A dedicated and accomplished physics professor who is committed to high quality education and advance the frontiers of knowledge in physics. Dr. Padma Suvarna, ma'am, we are very fortunate having you here today, ma'am. Now, I request you, ma'am, to take over the session. Ma'am, please carry on, ma'am.
Thank you. Thank you very much for speaking very nice words about me. At the outset, I would like to congratulate all the organizers for conducting really a very beautiful program, conducting this faculty development program on advanced materials, which is the need of the hour. And also, I would like to thank the organizers for giving me this opportunity. Thank you, Haripriya. Now, let me share my screen. Is it visible, Haripriya? Hello?
Visible, madam.
Okay, okay. Yes. Is it visible? Hello? Hello? Hello, Haripriya?
Visible, madam.
Okay, okay, fine. Yes, yes, yes. Okay. Today I am going to speak about ferroelectric properties of cobalt-based nanomaterials. These materials are having beautiful applications in optoelectronic devices and in some communications also. So I have chosen this topic. So this is the ferroelectric properties of cobalt-based nanomaterials. The main objective of this study is to synthesize cobalt-based nanoparticles by microwave processed sol gel technique, and also to study the structural and physical properties of the prepared nanoparticles. See, there are various techniques for the characterization of nanoparticles, like many conventional methods like a solid state reaction, sol gel is there, auto combustion, green nanotechnology, and co-precipitation technique for the synthesis of bulk as well as nanomaterials. Among all these methods, why sol gel is being used means the sol gel with the micro heating synthesis technique is adopted in the present work because of the rapid heating that can be obtained and low cost of sample preparation. See, at the end, the sample preparation should be very economical. So we have chosen this sol gel method along with microwave heating. This gives a very rapid heating. So we have opted that particular method. And once the sample is prepared, we'll study the structural and physical properties of the synthesized nanomaterials. So out of the different preparation methods available, the most commonly used sol gel method is used to synthesize these samples, followed by microwave heating. The method gives several advantages like low processing temperature, the production of ultra fine porous powders, and homogeneity of starting materials at molecular level. So what are the and also the sol gel technique is very popular wet chemical method which is broadly used for the preparation of inorganic materials, normally metal oxides, which are in the nano dimensions. You know, this process was first demonstrated in the 19th century, but it was practically proved by Stephen in the year 1931. This method includes the evaluation of inorganic systems through the formation of sol, which is a colloidal solution or precursor, and gelation of the sol to form a system in the continuous liquid phase known as a gel. Now, in order to prepare this cobalt-based nanomaterials, what are the materials that we have used means, that is glacial acetic acid, lead acetate, titanium butoxide, cobaltous nitrate, and lanthanum nitrate. So coming to the process of preparing this, so initially the samples are processed to make a dispersible oxide which forms a sol, that is a precursor, in contact with dilute acetic acid or water. Exclusion of the liquid from the sol yields the gel, and the solution or the gelation transition controls the shape and size of the particle. Calcination of the gel, it induces the oxide. One of the main advantage of this technique is the capability to regulate the microstructure of final product by controlling chemical reactions. It has been revealed that modification of the reaction conditions may considerably affect the structure of the sol gel product. This method is extensively used in the fabrication of inorganic and organic hybrid materials, and also it has an ability of producing nanorods, nanoparticles, monoliths, and thin films. Even in the present work, we have obtained 5 nanorods that I'll show you in one of the SEM images. So, as a whole, microwave technique is a rapid heating method in which the material absorbs microwave energy and is converted into heat energy within the sample volume. Therefore, very short period of time is consumed for heating the sample. See, if in the conventional methods, usually in order to heat the sample, very huge time is required. But in the present method, very short period of time is consumed for heating the sample. Microwaves can be used to carry out selective heating, which is not possible by using conventional heat treatments. Microwave heating produces potentially a cleaner, faster, and cheaper heating aid. This is also being used in food industry for decades. In recent years, this method has been used in scientific laboratories for accelerating organic reactions. So coming to the preparation, initially the materials were taken according to their stoichiometric ratio, and the precursor materials were lead acetate, cobalt nitrate, lanthanum nitrate, and titanium butoxide. So initially all these compounds were selected corresponding to the stoichiometric ratio, and the glacial acetic acid was taken as a solvent here. The glacial acetic acid solution was poured into a container and placed on the magnetic stirrer for persistently mixing the content. Later, lead acetate was added and dissolved in the solvent. After it was completely dissolved, this cobaltous nitrate and lanthanum nitrate was added to the same solvent, and the temperature was maintained at 50 degrees centigrade during the whole process. After this is continued for half an hour, titanium butoxide was added drop by drop to that persistently, and the entire solution was allowed to mix carefully for 2 hours, and the solution of ethanol and water was added to the solution. After some time, a gel-like solution was attained. This gel was drained naturally for nearly 2 days, that is 48 hours. After that, with the help of hot air oven for about 1 hour. Through this process, a rigid crystal form was acquired, which was grinded into a fine powder. Then, the attained powder was sintered at 750 degrees centigrade by a microwave furnace for around 1 hour. Further, the crystalline powder was grinded again to get fine powder. Then the pellets are prepared by maintaining pressure of around 10 torr in the hydraulic press. In addition, the prepared samples were synthesized using several techniques like X-ray diffraction, field emission scanning, electron microscope, etc. So once the materials are prepared, finally it should be synthesized for studying many things like size of the nanoparticles, what is the strain it can withstand, so on and so forth. So that should be characterized. So these are the characterization techniques we have employed. For structural analysis, X-ray diffraction is used, and for studying the surface morphology of the samples, we used FESM and TEM, and UV visible and FTR studies are performed in order to study the optical properties. Also studied the dielectric and ferroelectric properties. So for the structural analysis, we have used Bruker X-ray powder diffractometer having a wavelength of 0.15406 nanometers, and remaining all these characterization synthesis techniques are being used. So these are the this is the initial sample we have prepared: cobalt doped lead titanate nanoparticles. By varying the content of this between zero point 0.2 to zero point 0.8, after preparation of the sample, these are the synthesis techniques we have. These are the analytical techniques we have used: XRD, FESM, TEM, FDR, UV visible, dielectric properties, and finally, to study its magnetic properties, we have also done PE loop analysis. So, coming to this X-ray diffraction. So, initially, in order to study the size of the particles, the synthesized powder has been analyzed by using X-ray diffractometer. X-ray diffraction analysis was carried out to characterize the crystalline nature and also structure of the prepared sample. The XRD spectrum was recorded with the help of Bruker D8 X-ray diffractometer having a radiation of wavelength 1.542 angstroms. The X-ray was scanned over the titanate samples in the range of 2 theta between 10 to 90 degrees with a scan rate of 0.02 degrees. The obtained diffraction pattern was used to detect the crystalline phases in the specimen in analyzing the sample's structural properties. See, this X-ray diffraction gives information not only about the crystalline structure, but also the crystallite size, lattice parameter, and strain of prepared nanoparticles, prepared samples. So this is the XRD pattern that is obtained for the sample. The present figure depicts the XRD pattern of microwave processed lead cobalt titanate nanoparticles prepared by sol gel method by varying the cobalt content from 0.2. Here it has been shown that from 0.2 to 0.8. So this is the XRD pattern for 0.2. This represents for 0.4, and this is for 0.6 and 0.8. See the structural transformation to rhombohedral from a tetragonal phase during the variation of cobalt content. It has been confirmed from the XRD patterns. Also, here we can observe that up to 0.6 of cobalt content, the phases were enriched with the tetragonal phase, and also interestingly, it exhibits fine rhombohedral phases, and in addition to that, few tetragonal phases were also identified. It can be detected from the figure that at around 32 degrees, maximum intense peaks for 0.2 to 0.6 of cobalt composition. It has given the wide full width half maxima or beta, and also peak slit nature. See, this may be a sign for the presence of nanocrystalline structure as well as phase transformation. These two things can be seen very clearly at 32 degrees. The Miller indices of both tetragonal and rhombohedral phases were also mentioned. These two phases, tetragonal and rhombohedral phases of this PCT nanoparticles, were also inconsistent with the standard JCPDES file of this number 77-1373. Usually, this COTIO3 shows the rhombohedral phase and structure, but in the present study, at CO of 0.8 composition, it exhibits the formation of rhombohedral phase dominating the tetragonal phase. With the help of this Debye-Scherrer expression, full width, the crystallite size was calculated from full width half maximum of all reflected peaks. It was found that mean crystallite size of all samples has decreased from 14 to 17 nanometers by increasing the cobalt content. As the cobalt content is increased, the size of the nanoparticles has reduced to 7 nanometers. The reason for this is the rising value of the microstrain from 0.026 to 0.033, which is responsible for this reduction of the particle size. So this is the expression used to find out the crystallite size. So crystallite size was decreased from 14 to 7 nanometers with the increase of cobalt concentration. We can also find out the microstrain as well as the lattice constant using this particular formula. And also X-ray density and porosity can also be determined. So the lattice constant AB, the lattice constants A, B, and C were determined for the tetragonal reflection planes of the concentrations 0.2, 0.4, and 0.6 using the expression. This one 1 by d square is equals to h square plus k square divided by a square plus 1 by c square, where d is the interplanar distance and hkl are the Miller indices. So the outcome of this, from the outcome we can say that ABC values are found to be reducing consistently from 0.57 to 0.49 and 0.67 to 0.54 by varying the cobalt concentration from 0.2 to 0.6. It may be achieved due to the substitution of lead cations of high ionic radius by the cobalt cations of small ionic radius. Also, for this 0.8 concentration, which is in the rhombohedral phase, composition entrenched the ABC values, which is 0.5 and 1.37. The occupation of titanium cations by cobalt cations may strengthen the structural transformation and leap up to the lattice constants. Further, the porosity was also evaluated. Apart from the lattice constant, the porosity was also evaluated. The obtained result shows that the porosity, it was behaving like the porosity has been calculated using the formula. The porosity achieved the values increasing from 13.1 to 27.3%. The porosity, it will have an influence on various magnetic, electrical, and ferroelectric properties. Apart from that, the specific surface area also plays a key role in strengthening the electrical and magnetic properties. In the present study, the specific surface area is found to vary from 14 to 22 meter square per gram. This sort of large S values may be estimated to increase the different properties, whereas smaller values of S decreases all the properties of the samples. These are some of the properties these are some of the parameters which can be determined from X-ray diffraction. And coming to FESEM analysis, field electron scanning electron microscope. So field emission scanning electron microscope is used to study the surface morphology of lead, cobalt, titanate nanomaterials in powder form by changing the cobalt content from 0.2 to 0.8. So you can see the images that we have obtained for different proportions of cobalt, 0.2, 0.4, 0.6, and 0.8. So from the images, it is evident that for all the samples, the agglomerated PCT nanoparticles were formed, and also stone-like grains were observed. For especially for zero point 0.6 cobalt content, the formed grains were appeared almost in the spherical shape. Here you can see the spherical shape very clearly. The grain size was observed to be reducing with rise in the cobalt content. So you see here in the 0.2 concentration of cobalt, grain size is large, a bit decreased, and finally when cobalt concentration is 0.8, the grain size has been reduced considerably. Though the grain size is found to be reduced. So initially it was raised to 93 nanometers, and later it was reduced to 82 nanometers. So these are the values that we have calculated from FESM. And coming to TEM analysis. See here we can see the TEM images of microheated PCT nanoparticles by varying the cobalt content. The grain size of all compositions was found to be varying randomly between 26.1 to 78.9 nanometers. The PCT nanoparticles with 0.2 to 0.6 contents, it has revealed the shape of the particles, and it was like irregular flat plates, while 0.8 content exhibited the regular spheres. See here, these are all the samples appears to be flat up to 0.6, but here we can see somewhat the samples are having the spherical shape here. So what is the reason for this spherical shape here is the magnetic interactions among the PCT nanoparticles may be responsible for the agglomeration that has been observed in these images. Coming to the FTIR analysis, the FTIR spectra of the prepared nanoparticles traced between the wavelengths. Here we have traced between the wavelengths, wavelength up to 4,000 and 4,000 per centimeter. In general, the FTIR spectra will be very helpful for observing the presence of MO bonds, stretching vibrational frequencies, and the functional groups. It is clear that the wave numbers of A site and B site of MO bonds observed to be altering between 400 to 500 centimeters. From the results, it is clear that the ionic radius of lead and cobalt, ionic radius of lead is found to be 1.2 angstroms. CO2 plus is found to be 0.58 angstroms. Titanium 4 plus is found to be 0.68 angstroms, and O2 is found to be 1.32 angstroms. In case of lead-based perovskite ceramics, cobalt cations substitute the lead cations instead of titanium cations. Hence, the magnetic cations such as cobalt, iron, nickel, etc., they prefer to occupy A site only. Consequently, the constant VB value was it is clearly evident. Further, the peaks at 1724 per centimeter, 3,394 per centimeter, and 3,721 per centimeter were occurred owing to the OH stretching and bending vibrations of H2O molecules absorbed by PCT nanoparticles. So from this we can find the vibration frequencies of the particles that occupy A and B sites. Coming to the UV visible analysis, the optical band gap, with the help of this UV visible spectrometer, we can find out the optical band gap of the synthesized samples. So the optical band gap energies of the samples that has been synthesized by varying the cobalt with the composition of 0.2 to 0.8 compositions were determined and assuming the linear portion of the curve in the direction of x-axis as the absorption coefficient alpha approaches to 0. On the x-axis we have taken alpha h nu, and on the y-axis we have taken alpha h nu whole square. It was clear from the graph that alpha h nu whole square against the photon energy has been drawn for various samples. The direct band gap of the nanoparticles is found to be almost similar, that is around at 3 electrons. See, for all these 4 samples, we can see that the band gap is found to be almost similar, almost, not exactly, almost similar. However, the band gaps apparently increased with change in decimal positions for cobalt content. From this, we can say that there is no considerable variation in the EG values, and this kind of narrow band gaps may be obtained due to the enriched lead content. But the increasing of optical band gap up to 3.06 electron volts has been achieved for x equal to 0.8 composition, which may be due to enriched cobalt content. See, for this sample, this is less than 0.3. It is almost nearer to 3. Here also this is nearer to 3. Whereas here this is 3.06 electron volts, which is due to the increase in the cobalt concentration. So, it can be expected that the microwave heating could be responsible for the increase of EG value for the same composition. Thus, PCT nanoparticles, it may reveal wide applications in photocatalytic operations, sensor and optoelectronic devices based applications because of the narrow and wide band gaps. Coming to dielectric studies, here the dielectric parameters like epsilon dash and epsilon double dash and AC conductivity were investigated in terms of frequency and composition. The frequency dependence of dielectric constant and the dielectric loss has been, these two things are being shown here. Here in this one, we can see this is a plot between epsilon dash versus frequency, and another one will be the dielectric constant. Here it is observed that particularly when x equal to 0.6 and 0.8 compositions, epsilon dash was found to be 4354 and 2450 at 100 hertz. And similarly, this is the plot between epsilon double dash and the frequency. This epsilon double dash values also found to be 4575 and 2657 for the same compositions. See, in general, at smaller frequencies, the grain boundaries become more active, whereas grains were more active at larger frequencies. This has been reported in literature. From this, we can say that grains exhibit a low resistivity, whereas grain boundaries, they will exhibit high resistivity. The present samples, they showed high magnitude of epsilon dash and epsilon double dash at lower frequencies. Also, the space charges become more dominant at a small frequency. As a result, large amount of polarization will be induced, leading to high epsilon dash and epsilon double dash. When we move towards high frequencies, the epsilon dash along with epsilon double dash parameters were reduced and they remain almost constant. See, the reason for this may be due to lagging of space charge carriers behind the applied electric field with the increase in frequencies. So as a whole, we can say that the inhomogeneous dielectric structure is accountable for this behavior of epsilon dash and dielectric loss epsilon double dash with frequency. Large epsilon dash and epsilon double dash values for these two combinations, that is x equal to 0.6 and 0.8, was recorded at a megahertz frequency range, which may be suitable for dielectric absorber applications at larger frequencies. Now we have also determined the AC conductivity. So all these studies were done using LCR height tester, which is available in our laboratory. The frequency dependence of AC electrical conductivity is shown in the figure. From the graphs drawn for frequency versus AC conductivity, it is at different compositions of 0.2 to 0.8 has been shown here. This has been done at a up to a frequency of 50 kilohertz. So after 70 kilohertz, for x equal to 0.2 and x equal to 0.4 samples, they exhibited small relaxation behavior, and above relaxation frequency of 70 kilohertz, the swing type trajectory of the graph was obtained. The reason for this is due to matching of jumping frequency of charge carriers. The trapped charge carriers within the dislocation centers, interfaces, and the lattice distortions may be accountable for this sort of behavior. And for x equal to 0.6 and 0.8 compositions, they exhibited an exponential increase up to 399 kilohertz. Above resonance frequency of 399 kilohertz, a gentle decay was noticed for both 0.6 and 0.8 samples, compositions, 0.6 and 0.8. But 0.4 sample described higher electrical conductivity than all the remaining samples. Coming to the study of ferroelectric properties. The ferroelectric hysteresis behavior of the synthesized PCT nanoparticles is studied with the help of polarization, electric field loop tracer. These observations were recorded after connecting the pellet parallel to 4 microfarad capacitors in order to compensate the PE loop tracer. So it is seen that all the prepared nanoparticles exhibited explicit hysteresis loop, and explicit hysteresis loop distorted into banana shape shown at room temperature. This in turn induces the leakage current that can be ascribed that may be due to oxygen vacancies on the top surface of the grains in spite of polarization. The saturation polarization from this PE loop, the saturation polarization, coercive field, and the remanence polarization of the lead cobalt titanate particles has been studied. The values of ferroelectric parameters expressed that the saturation polarization was shifting to 1.74 microcoulombs per centimeter square from 0.042 with rising CO composition. This type of random variation of PS is due to quick and partial response of charges for the input field frequency. The coercive field as a function of composition was also shown. This coercive field observed to be changing for all the CO based, for all the CO doped lead titanate nanoparticles. So finally, we can conclude that for this lead cobalt titanate nanoparticles with changing cobalt content from 0.2 to 0.8, the mean crystallite size has been reduced to 7 nanometers from 14 nanometers by varying cobalt content. And the SEM and TEM revealed the formation of a flat stone and plate-like nanoparticles. Large differences between particle size and crystallite size, it may be due to agglomeration. From the FTIR studies, it has been revealed that the existence of lead oxygen, cobalt oxygen, and titanate oxygen bonds at A and B sites. And from UV visible spectra, the band gap was found to be 3.06 electron volts. From it has been increased from 2.08 to 3.06 electron volts, and the dielectric parameters like epsilon dash, epsilon double dash, and conductivity was also determined. It is observed that 0.4 composition exhibited maximum conductivity. The saturation polarization is varying from 0.042 to 1.74 micro coulombs per centimeter square with the rise of the cobalt content. So similarly, we have synthesized initially we have synthesized PCT nanoparticles. Next, we have synthesized lead cobalt lanthanum titanate nanoparticles. And after, by varying the concentration from 0.05 to 0.2, after synthesizing this, the samples has been analyzed by using the XRD, FESM, TEM, FTR, U visible, and we have studied the dielectric properties and also its magnetic properties by using this hysteresis loop analysis. So samples were synthesized in the similar manner as we have synthesized PCT nanoparticles by using sol gel method and followed by micro heating. So coming to this XRD analysis, the XRD patterns are shown here. From the XRD pattern, it is clear that the prepared nanoparticles, here we are changing the lanthanum composition. Earlier we have changed the cobalt composition, now we are going to change the lanthanum composition from 0.05 to 0.2 with respect to alteration of cobalt composition. It has revealed the formation of a few tetragonal phases of PT structure. These tetragonal and cubic phases they are found to be incompatible with the standard JCPDS files as I have represented here with the file number. The cubic reflection planes were represented in the X-ray diffraction plane pattern. It is clear that there was an absolute transformation of a unit cell to cubic structure from tetragonal. Which means that as the lead cations were varied with the corresponding lanthanum cations, the PCLT nanoparticles exhibited tetragonal phases, and at the same time, cubic reflection planes achieved they have achieved the required phases by altering the cobalt content with respect to the lanthanum content. However, this entrenched the fact this explains the fact that change of small concentration of cobalt cations can exhibit they may dominate rather than the variation of lead cations. Also, the fine crystallinity and broad width of diffraction peaks were observed. So this fine crystallinity and broad width of the diffraction peaks, they explain the presence of nano-sized particles and crystallites. The mean crystallite size was found to be altering around 24 to 38 nanometers. This reduction may be due to reducing in terms of this lanthanum component, which may be due to the rising trend of developed microstrain due to sol-gel preparation and micro-heating reaction. Moreover, the lattice constants were calculated. It also shows that the lattice constant also reduced from 0.38 to reduced to 0.38 from 0.39 nanometers, which may be due to the occupancy of titanium cations only at B sites. You know, earlier the same type of cation occupancy was reported in the literature. It is revealed that the ionic radius of lead is 1.2 angstroms, cobalt is 0.5 angstroms, lanthanum is 1.01 angstroms, and titanium is 0.68 angstroms. Also, the magnetic cations such as nickel and manganese, etc., will have the possibility of occupying the A site. So coming to FESM analysis, this is the images of PCLT nanoparticles taken from SEM. Here also the titanium composition has been changed from 0.05 to 0.2. So from the images, it is clear that for 0.05 and zero point 0.1 samples, they exhibited inhomogeneous distribution of stone type grains. For y equal to 0.15 content, it shows it exhibits few square and stone like grains having a homogeneous distribution. For 0.15, this exhibits, this is somewhat homogeneous and is also having a stone-like grains. In the similar y equal to 0.2 sample contained a gentle distortion of inhomogeneous grains. This is the FTIR analysis of the FTIR spectra for this PCLT nanoparticles. So this shows the wave number ranging from 4000 to 400 per centimeter. Usually FTR, it gives the information about the existence of MO bonds, functional groups along with the vibrational frequencies. But from the figure it is evident that nu A and nu A of A site and nu B of B site were recorded to be altering from 408 to 512 centimeters. Increasing of y value from 0.05 to 0.2, it causes the shifting of nu A towards the lower values from 512 to 417 per centimeter. This may be due to favorable occupation of cobalt, lanthanum, and lead ions at A site. Besides that, at B site, the occupancy of T ions justifies the constant wave number of 408 per centimeter. Apart from this, some additional absorption spectral lines were observed at wave numbers of 1373 and 1489 per centimeter, which may be due to bending vibrations of OH bonds. Also, due to OH absorbed by the samples. And the peaks noticed at 1630 and 3614 per centimeter were derived due to OH stretching and bending vibrations of H2O molecules. So coming to the UV visible spectral analysis. So to obtain the optical band gap, we have taken the linear portion of the curve in the direction of a photon energy, where accurately the alpha tends to 0. So from the graph, it is clear that the band gaps of y equal to 0.05 and 0.1 contents were found to be approximately 3 electron volts. 0.05 and 0.1 found to be exactly 3 electron volts. It was indicated that the smaller lanthanum content was not capable to establish a sufficient modification in the energy gap. But for y equal to 0.5 content, it exhibited a narrow optical band gap of almost 2.32 electron volts per 0. Here we can notice this one at for 0.15 composition, energy band gap is found to be 2.32 electron volts. In addition, at y equal to zero point 0.2, the wide band gap of almost 3.2 electron volts is observed. Narrow and wide band gaps were obtained based on the cation exchange in between A and B sites. See, the microheating may also be accountable for this in some cases. So this sort of materials having wide and narrow band gaps, they are useful in optoelectronic devices, sensors, and photocatalytic instruments. So this is having a smaller band gap and this is having a wide band gap. And coming to the dielectric properties, so there are dielectric properties like epsilon dash and epsilon double dash were studied. So both this epsilon dash and epsilon double dash exhibited higher values at lower frequencies. Specifically, y equal to 0.15 and 0.2 contents expressed epsilon dash at about 700 and 1600 at a frequency range of 100 hertz. Similarly, epsilon double dash values are found to be at 4250 and 2417 for the same frequency. So the grain boundaries seem to be more active at lower frequencies, as if grains exhibit more activeness at larger frequencies. This has been reported in the literature. It is also known that uh, grain boundaries describe large resistivity while the grains reveal low resistivity. Hence, all the samples revealed high values of epsilon dash and epsilon double dash at lower frequencies. Further, the space charges is found to be dominant at a low frequency, which leads to large values of polarization and hence larger epsilon dash and epsilon double dash. When the frequencies are moving towards higher values of epsilon dash as well as epsilon double dash, uh, they reduces and remains almost a constant. This can be due to lagging of space charge carriers following the applied field with increment in frequencies. As a whole, the inhomogeneous dielectric structure is accountable for this type of nature of epsilon dash and epsilon double dash with frequencies. But large epsilon dash and epsilon double dash values for the concentrations of 0.15 and 0.2 computed at megahertz frequency range may be suitable for dielectric absorber applications at high frequencies. Coming to AC conductivity, it is evident from the graph that y equal to 0.05 and zero point 0.1 compositions exhibited a systematical rising behavior up to 50 kilohertz. Above that, two samples exhibited a small relaxation behavior, and after relaxation frequency, it was observed as a flat trajectory. This may be due to corresponding of jumping frequency of charge carriers. You know, sometimes the trapped charge carriers which are existed in dislocation centers, lattice distortions, and interfaces maybe reason may also be reason for this. Besides, I mean, for y equal to 0.15 and zero point 0.2 contents exhibited an exponential increase in the behavior up to the frequency of 4 megahertz. Above the resonance frequency FR equal to 4 megahertz, gradual decay was noticed for both the compositions. These two samples exhibited higher electrical conductivity among all samples. Hence, this can be from this this can be established that the development of nanofibers may acquire high electrical conductivity. That they may exhibit very high electrical conductivity. Coming to the ferroelectric properties, see, it is very clear that the four samples they exhibit, they show very distinct hysteresis loops. The saturation polarization value is almost constant at 0.0039 microcoulomb per centimeters as long the uh, is found to be constant. It was indicated that saturation polarization has values has no observable changes for all the compositions because the charge carriers have equal response to the applied AC field. But interestingly, in some cases, the small value of polarization exhibited, which may be due to current leakage and the formed oxygen vacancies. Similarly, the remnant polarization was noted to be 0.039 microcoulomb per centimeter square for all the samples, except y equal to 0.15 content. Hence, the samples may be desirable for ferroelectric capacitors and memory capacitors. Hence, we can conclude that for this samples doped with the lanthanum, whose concentration is varying from 0.05 to 0.2 in steps of 0.05. These nanoparticles were prepared using sol gel via micro heating. The prepared nanoparticles exhibited cubic phases, including some tetragonal lead titanate phases confirmed by XRD. The FESM analysis explored stone-like grains with large diameters, altering to 174 nanometers. And from the UV visible spectra, it is observed that energy gap is varying between 0.32 to 3.2 electron volts, and dielectric properties like epsilon dash and epsilon double dash were studied as a function of frequency. Both these parameters exhibited large values at small frequencies, and the hysteresis loops were also noted. From this, it is observed that they showed high value of coercive field. In addition, y equal to 1 and 0.1 and zero point 0.2 exhibited high epsilon dash values in magnitude. Hence, we can say that these substances are more suitable for ferroelectric memory applications. These particular PCLT nanometals are found to be applicable for ferroelectric memory applications. These are the parameters which we have obtained from this PE loop. So coming to the to another lead-based lead cobalt titanate nanoparticles, here we have taken effect of, here we have observed the effect of lanthanum. So here also the samples are prepared by means of by microprocessed sol gel route, and then the structure of the present samples is confirmed by diffraction pattern and compared with the standard JCPDS pattern. The structural parameters like a lattice constant, average crystallite size, theoretical density, porosity, dislocation density, and strain are also estimated. The morphology is analyzed using sum and temp, and the optical properties such as A, B, site wave numbers, force constants, and optical band gap energies are studied by FTIR and UV visible spectrometers. The dielectric properties such as dielectric loss, dielectric constant, dielectric loss, and AC conductivity was explained in terms of, was examined in terms of frequency. And by using PE loops, the ferroelectric property of the prepared samples is studied. So coming to the XRD analysis, so this is the XRD pattern for the prepared PCT nanoparticle. So from the XRD pattern, it is confirmed that the reflection planes like 002, 004, 100, 008 up to 203 of PLCT nanoparticles with varying lanthanum content. Here we have varied the lanthanum content from 0. 0.2 to 0.8 with respect to the variation of lead content, and all the planes are found to be in good agreement with the standard tetragonal phases of lead titanate and cobalt lanthanum titanate. They are in agreement with the JCPDS data. The number is shown here. The investigation on XRD pattern revealed broad diffraction peaks, which in turn is due to the presence of nanocrystals. Besides that, Z equal to 0.2 and 0.4 contents confirmed the phase transition, confirmed the phase formation with the fine crystallinity. Maximum intense peaks were computed at an angle of 2 theta around 32.176 degrees. High lead content plays an important role to obtain the lead titanate structure of these two samples, whereas for Z equal to 0.6 and 0.8 contents, the maximum intense peaks were identified at 32.176 degrees. For these samples, the maximum intense peaks were observed at 6.407 degrees. See here, somewhere here we can see the maximum peak. It may be achieved because of the existence of enriched lanthanum content. Therefore, Z equal to 0.6 and 0.8 contents, they ascribed the tetragonal structure of CLT matches with the JCPDS files having the number. Finally, from the investigation of this PLCT nanoparticles, XRD patterns, it is known that larger concentrations dominate the structure formation. Further, the structural parameters such as ABC, that is lattice constants, crystallite size, bulk density, X-ray density, porosity, volume of the unit cell, and specific surface area are also calculated. It is found that the lattice parameters were reducing with the increment of lanthanum composition, which may be due to small ionic radius of lanthanum cations rather than lead cations. The unit cell volume was found to be reducing as function of substituent concentration. This may be due to decrease in lattice constant with increment in Z value. The mean crystallite size D was found by Debye method. And the mean crystallite size was noticed to be varying from 10.50 to 15.50 nanometers. The crystallite size varied randomly as a function of lanthanum content. Coming to this FESM analysis, see from the images of the FESM, it is observed that all compositions possess inhomogeneous distribution of grains. Besides that, distinct stone shaped particles, here we can see somewhat stone shaped particles were noticed for Z is equals to 0.2 and 0.4 compositions. Spear like grains were found for 0.6 composition. For 0.8 composition, nanofibers were formed. See here you can find at x equal to 0.8, we can see small nanofibers. This is the uniqueness of the work, which may be due to diminishing lead content. Okay. This is the HR10 images of HR10. Then from the 10 images, these nanofibers are even more clear. So from the images, it is evident that the partial formation of nanofibers started at z equal to 0.2 and ended with absolute formation of nanofibers at z equal to 0.8 content. For z equal to 0.2 to 0.4 compositions, unsystematically aligned spaghetti type nanofibers. Also, some distorted spherical grains were observed among these nanofibers. While raising the lanthanum compositions above zero point 0.4, the elongated nanofibers were formed. Some of those nanofibers exhibited the bending nature. Those can be generally suitable for drug delivery applications. Few fibers appeared like a rod and large stretched out platelets. The average particle size was noticed to be altering between 13 to 18 nanometers. So it can conclude the formation of nanofibers by using microwave processed sol-gel technique, which is an interesting aspect here. See, the formation of nanofibers may normally be assumed to develop the electrical conductivity of corresponding specimens. Coming to the FTIR analysis. So from the spectra, it is clear that the wave numbers nu1 and nu2, that is at A site and B site, MO bonds are found to be altering from 400 to 500 per centimeter. So nu I decreases from 504 to 424 per centimeter, which may be due to lead, lanthanum, and cobalt cationic occupancy at A site with increase of lanthanum content. Besides that, the value of nu2 was observed to be almost constant around 409 per centimeter. This may be due to the occupancy of Ti cations at B site only. FDR also exhibited different absorption bands located at 1354 and 1489 per centimeter, which signifies the bending vibration of OH bond, and these were related to OH bonds absorbed by APLCT nanoparticles. Coming to its optical band gap. So the optical band gap energies of Z equal to 0.2 to 0.8 compositions were determined on extrapolating the linear portion of the curve in the direction of x-axis as the absorption coefficient alpha approaches to 0. It is clear that the direct band gap of Z equal to 0.2 to 0.6 nanofibers were found to be almost similar at around 1.5 electron volts. However, the band gaps were apparently increasing by acquiring change in decimal positions with lanthanum content. This implies that there was no considerable variation in the optical band gap energy values. This kind of narrow band gaps may be obtained owing to enriched lead content. But interestingly, the increase in optical band gap of 3.44 was achieved for Z is equal to zero point 0.8 composition, which may be due to increased lanthanum content. The obtained wide bandgap value for Z equal to 0.8 composition may be argued due to the cation exchange. So it can be expected that the microheating could be responsible for increase of optical bandgap energy values for the same composition. Thus, this PLCT nanofibers may reveal wide applications in sensors, optoelectronic devices, and photocatalytic applications because of narrow and wide band gaps. The color of samples are also found to be changed. The first two samples, that is Z equals to 0.2 and zero point 0.4, are found to be in light brown color, whereas the third one, that is for Z equal to 0.6 combination, is found to be thick brown color, while the last sample, Z equal to 0.8, is found to be in pure white color. This confirmed that there is a color change from sample to sample, and it might also be a reason for partial change of optical band gap energies in case of Z equal to 0.2 to zero point 0.6 contents, and hues enhancement of the same for Z equal to 0.8 content. So coming to the dielectric studies, so from the plots, it is clear that epsilon dash and epsilon double dash values are found to be higher at smaller frequencies, whereas small values at high frequencies may be owing to the inhomogeneous dielectric structure. Consequently, the high epsilon double dash was owing to the contribution of grains at low frequencies. Besides that, grain boundaries may be accountable for the small value of dielectric constant at larger frequencies. It is also observed that dielectric constant and dielectric loss exhibited high values at smaller frequencies, especially for concentrations of 0.2 and 0.6, executed the dielectric constant values around 900 and 1300 at 100 Hz. Similarly, dielectric loss was observed to be 2600 and 13,000 for the same 0.2 and 0.6 concentrations. In general, the grain boundaries are seemed to be more active at low frequencies, and also grains exhibited more activeness at larger frequencies. Also, grain boundaries exhibit large resistivity while the grains reveal low resistivity. So, as a whole, the inhomogeneous dielectric structure is accountable for this type of nature of dielectric constant and dielectric loss with the frequency. The high dielectric loss values are observed at lower frequencies, whereas the smaller dielectric constant values are noticed at high frequencies. Similar trend was observed in dependence of dielectric constant on the frequency for all compositions. Hence, at higher frequencies, all these samples may ensure substantial contribution as a dielectric absorbers. So coming to the AC conductivity analysis. So the frequency dependence of AC conductivity is displayed here. From the plot, it is clear that all the samples revealed gradual increasing nature up to 60 kilohertz. Beyond 60 kilohertz for Z equal to 0.4, it disclosed a small relaxation, and above relaxation frequency FR equal to 60 kilohertz, the fluctuated light trajectory was noticed. This may be due to matching of jumping frequency of charge carriers. Sometimes the trapped charge carriers within the interfaces, dislocation centers, and the lattice distortions may be accountable for this. In addition, for Z equal to 0.2, 0.4, and 0.8 concentrations, they exhibited an exponential increasing behavior up to 3.7 megahertz. After resonance frequency of 3.7 megahertz, slow drop has been observed. It is noticed for all the compositions, though these samples induced larger AC conductivities than the rest of the samples. Besides that, for Z equal to 0.8 composition, drastic and exponential rise of AC conductivity was noticed, and it was observed to be 7.5 into 10 to the power of minus 6 Siemens per centimeter. Hence, we can say that the formation of nanofibers may attribute this high AC conductivity. Coming to the ferroelectric properties, the ferroelectric nature of a PLCT nanofibers as a function of lanthanum composition was studied here, using the plots of polarization against the applied electric field. It is understood that the PE loops of Z equal to 0.2 to 0.8 contents, they are exhibiting well-defined hysteresis loops. Besides these hysteresis loops, they exhibited a distorted banana shape. It can normally create the leakage current, which may be due to the formed oxygen vacancies on the upper surface of the grains instead of polarization. The ferroelectric parameters like saturation, polarization, coercive field, and remnant polarization of these PLCT nanofibers are also determined as a function of substituent. The coercive field is found to be varying from 0.54 to 0.68. Similarly, saturation magnetization is found to be changing from 0.36 to 0.39, and also remnant polarization also varies from 0.36 to 0.39. So all these variations may be due to unsystematic, they are all found to be unsystematic due to quick as well as partial response of charge carriers for the provided input electric field. Hence, we can conclude that these PLCT nanofibers, they are prepared using a microwave processed solder technique. XRD investigations confirmed the occurrence of tetragonal PT and LCT phases. The phase transformation from tetragonal PT to tetragonal LCT phases at Z equal to 0.8 composition was attained. The FUSM and HR term, they established that there is a clear indication for the formation of complete nanofibers at Z equal to 0.8. Hence, these nanofibers, they exhibit their potential applications in drug delivery systems. FTR studies reveals the presence of MO band. The optical band gap is found to be 3.44 electron volts. Hence, it reveals the photocatalytic activity of the composition. The dielectric properties like epsilon dash and epsilon double dash also determined. They are found to be very high, especially for Z equal to 0.2 and 0.6 contents. Executed epsilon dash values around 900 and 1300 at 100 heads. Similarly, frequency dependence of AC conductivity is also investigated. For Z equal to 0.8, it is found to be around 7.5 to the power of minus 6 Siemens per centimeter. From the PE loops of 0.2 to 0.8 contents, they exhibited well-defined hysteresis loops. However, these loops are distorted into banana shape, and further the leakage current is being created because of the formed oxygen vacancies on the upper surface of the grains in spite of polarization. So from all the above things, it is observed that. So from the work carried out on the lead-based titanides, it is observed that it exhibits good dielectric and optical properties and also excellent conductivity. It is evident that some of the from the literature, actually, it is evident that some of the composites exhibit excellent dielectric properties and is suitable for AMI applications. Hence, with this background, uh, these materials can be utilized for EMI applications as a very good microwave absorbers. So this is the work that has been carried out in our lab by my research scholar. So this entire credit goes to him. He is Mr. N. Suresh Kumar. Okay. Thank you all for your patient listening. Thank you.
Thank you, ma'am. Thank you for your wonderful and insightful speech, ma'am. Ma'am, here in the chat box, we have questions, ma'am. Can I read, ma'am?
Yes.
Okay, ma'am. The first question: how does the microstrain affect the structure of the material? Once
Pardon?
again, I'll read,
Yeah,
ma'am.
yeah.
How does the microstrain affect the structure of the material?
See, it all depends on the occupation of different sites by the particles. Hence, it affects the microstrain as well as the structure. It all depends on the occupation of different sites by the lead as well as the cobalt nanoparticles. You do one thing. Hello, Haripriya.
Ma'am, tell me, ma'am.
You give my mail ID to them. Ask them to send a mail.
Oh, okay, ma'am. Okay, ma'am.
Okay.
Okay, ma'am. Ma'am, next question is there, ma'am. Can I read, ma'am?
Haripriya, I have a meeting now. So ask them to send a mail to me. Okay.
Okay, ma'am. Okay, ma'am. Okay, ma'am.
You have
Now I
meeting at
request,
12:15.
ma'am, now I request co-convener Mr. Shivaya, Assistant Professor in Physics, to propose the vote of thanks.
Thank you, madam. On behalf of H&S department, today I take this opportunity to put all my gratitude in the form of words. The first of all, I would like to thank our today eminent speakers and directors, sponsor research at JNTA, Professor R.Padma Suvarna garu, for accepting our request for giving such a wonderful presentation on ferroelectric properties of cobalt-based nanomaterial, nanoparticles, and making even meaningful and interesting. Thank you very much, Thank you very much, madam. I would like to express our profound gratitude to our principal, Dr. Saya Surya, madam, for her constant support and encouragement throughout the program. Thank you, madam. I would like to extend my heartfelt thanks to our beloved correspondent, Srimati V.K. Padma madam, for her encouraging words at the time of inaugural session. Thank you, madam. I would like to thank you our director, Srimati V.K. Srivani, madam, who has initiated us to this program and our continuous support right from its inception. Thank you, madam. I would like to express my gratitude to our managing director, Sri Raghunath Reddy sir. Thank you so much, sir, for supporting us, guiding us in right way. My heartfelt thanks to our convener, Haripriya madam, and her entire team, Jansi Rani madam, Jayaprakash sir, and Chandrasekhar sir, Suman Gopinath madam, Engineering madam, Vijayalakshmi madam, for this continuous support in making first day of this FDP successful. A big thanks to Noor sir and Nagendra sir, who is the backbone of this online session by providing technical support. Thank you, sir. Finally, at the end of the session, I would like to thank all the participants of this FDP for their glorious presence. Thank you, everyone.
Okay. Once again, I thank all the organizers for giving me this opportunity. Thank you.
Thank you, madam.